In this lesson, we're going to discuss how to perform hypothesis testing for population proportion problems. Now, a proportion is the fraction or percentage of a population having a particular trait of interest. Now, down here we have a few examples of typical problems that you would see that you can identify as population proportion problems. Now also keep in mind that when you see the word proportion in a problem, well, that indicates that you're going to use a population proportion hypothesis testing technique, but you may also see the word percent used. And that's because your percent is equal to the proportion times 100%. For example, if you're told that the proportion of people who are left-handed in your population is 0.1, well, that's the same as saying that 10% of the people in your population are left-handed. Now, here are some typical problems that you would see. For example, the percent of left-handed people in a population, the proportion of 12th grade females who feel that they are overweight, the percent of drivers who admit to running a stop sign, the proportion of patients who showed improvement in a drug trial, or the proportion of people who have brown eyes in a population. So you see, in all of these problems, you see either the word percent or proportion appearing. And that indicates that you want to use a hypothesis test for population proportions. And that's what we're going to go over right now. Now, for all of these problems, also keep in mind that we're going to use the normal distribution to calculate our critical regions and the p-values. Now, to perform hypothesis testing for a population proportion or percent problem, what you want to do is take a sample of size n and evaluate the quantity p hat, which is x divided by n, where x is the number of successful observations in your sample of size n. And you want to use that p hat as a point estimate to test against a hypothesized population proportion p0. So for example, if you take a sample of 50 people and you find that 6 of them are left-handed, then your point estimate p hat would be 6 divided by 50. And you would use this to test against a hypothesized population proportion of, perhaps 0.1. Now, it's a fact that these values that we have right here, p hat minus p0 divided by the square root of p0 times q0 over n, where the q0 is 1 minus p0, remember that from previously. These numbers will be approximately standard normally distributed, so normally distributed with the mean 0 and standard deviation 1, as long as n times p0 is bigger than 5 and n times q0 is bigger than 5. So as long as these two conditions are satisfied, these numbers will be standard normally distributed. And so what we can do then is use this value right here that we calculate as a test statistic, and also to determine p-values to decide whether or not to reject a null hypothesis like p equals p0. Now let's take a look at a summary of all of this. So right here we have a table summarizing everything that you'll need to perform hypothesis testing for population proportion problems. So as we've seen before, you'll have either a two-tailed test, a right-tailed test, or a left-tailed test. For the two-tailed test, you would have a null hypothesis, like P equals P naught, and you'll test that against the alternate that P does not equal P naught. This will be your test statistic that we saw previously. So you just calculate this quantity. That's going to be your test statistic. Then you can use this command in Excel to calculate your p-value. And if your p-value is less than your significance level, that's when you reject the null hypothesis. Alternatively, you could calculate a critical region right here. So you would calculate that value z alpha over 2, just like we saw before. And if your test statistic satisfies this inequality, then you would reject h naught. You can also have a right-tailed and a left-tailed test. For the right-tailed test, your alternate hypothesis would be that p is actually bigger than p naught. The true population proportion is actually bigger than p naught. You use the same test statistic, but this would be your command to calculate the p-value using Excel. And alternatively, you could calculate a critical region right here. So you would calculate that z alpha there using the same techniques that we used before. If your test statistic satisfies this inequality, you would also reject h naught. And then you have a left-tailed test that your true population proportion is equal to p naught. Your alternate would be that the true population proportion is actually less than p naught, and this would be your command that you would type into Excel to calculate your p-value. And you could also determine a critical region. You would calculate that z alpha, and then if your test statistic satisfies this inequality right here, then you would reject h naught. Now let's take a look at an example. So for this problem, from a previous study in Casper, Wyoming, the number of adults who admitted to running red lights during the prior 6 months was 53%. Now recently, many of the city's stoplights were replaced with newer LED versions, and the city would like to determine if the number of adults who admit to running red lights has changed. So they took a survey of 880 randomly selected adult drivers and found that 445 of them admitted to running red lights in the prior 6 months. Now that's after the new LED lights were installed. So at the 95% confidence level, we would like to test the claim that the number of adults who admitted to running a red light during the prior 6 months has changed as a result of the new lighting system. Now keep in mind for this problem, since we're dealing with a confidence level of 95%, that means that our alpha is going to be 0.05, and we see that our p hat value here is going to be 445 divided by 880. And that is approximately 0.506. So you see this number 0.506 is different from 0.53, but the question is it significantly different? That's what we have to determine. So let's take a look at the solution to our problem here. So the first thing we have to do is identify all of our variables. Well, the n is 880 in this case. Our p hat is going to be 445 over 880. You see the x is 445. Our alpha is 0.05, and p naught is going to be 0.53. Now let's set up our null and alternate hypotheses. Well, our null hypothesis is going to be that p equals 0.53. So we're assuming that nothing has changed from when the old lighting system was in place. Our alternate is going to be that the proportion of adults who admit to running red lights has changed. So it does not equal 0.53. Now notice the wording "has changed" was used in the problem, so that's why we're using a two-tailed test here. So the problem didn't tell us which particular direction we're expecting a change in the true population proportion, so we use a two-tailed test. Now we just have to calculate our test statistic, so right here it is. Notice we take p hat, right here's p hat, minus p naught. Divide that by the square root of 0.53 times 1 minus 0.53 over 880. If you calculate this using Excel or a calculator, you'll find that you get negative 1.445. Now we can use this to calculate our p-value. And our p-value, well, if you type this into Excel right here, this is the command that you would use. Recall the previous slide that we had looked at. This is our command for the p-value for a two-tailed test. If you evaluate this, you'll find that you get 0.148. And since 0.148 is greater than 0.05, we would fail to reject the null hypothesis. And then we could also conclude then that the data does not support the claim that the number of drivers who admitted to running red lights in the prior 6 months has changed. And so there you go. That's how we solve that problem.